Okay, so now we want to see if we can turn this into some sort of exploit, execute some code that wasn't intended by the developer. So again, if we list out our source code with the list command, remember that we have that third function overflowed that never gets called. You can think of that as some debugging code that just got left in. As we'll see later when we do our Windows examples, we won't always have this luxury. One, we won't have the source code, and two, there's nothing to say that there's going to be code lying around that we necessarily want to execute. We'll instead use some shellcode, so like the Metasploit payload system where we say we want Windows Meterpreter reverse TCP as our payload, then magically when we run, say, MSO8067, Metasploit just magically puts the payload in the right place and it executes, and we get our Meterpreter reverse shell. So we'll do that manually. We'll create some shellcode and drop it into our exploit in the correct place, and we'll learn all about that in our next exercise when we move over to Windows. But for now, again, we'll start with the basics, and all I want to do here is get execution hijacked printed out to the screen. Not as exciting as a reverse shell, of course, but it will be technically an exploit. So that's going to be what we want to do. So I need to know where overflowed is. Just because it isn't called doesn't mean it's not in memory. So if we disassemble overflowed, the first memory address of overflowed is here. See, our prologue here. So we push EBP. Remember EBP, to save the EBP from, say, main or whatever the current function is, pushed onto the stack. So that is the bottom of the new stack frame, and then we move ESP into EBP, and then subtract, in this case, 8 in hex from ESP. So again, moves ESP up. So basically we have ESP moved up, and then we have ESP adding some more space. So kind of beyond the scope of what we're doing here, but kind of how a new stack frame is made. If you're interested in exploit development, I certainly encourage you to learn some assembly and figure out how these programs work. It is going to vary a little bit from platform to platform, again, how this is implemented, but they pretty much all end up doing kind of the same thing. In the end, it's just how they implement it is a little bit different based on the platform. Alright, so let's go ahead and do what we're going to do. So we want to grab this address here, and instead of our 4 B's that just make it crash, we want to put that address of the first instruction in overflowed into our saved return address. So instead of going back to main, we'll be redirected to the beginning of overflowed, and it'll make execution hijacked execute. Alright, so let's do that. Again, we can go up to our little Python script here, and we tell it to run. We want to take out our b times 4. We can leave our a times 9 in. Remember, that's just padding to get to the offset of the return address. We have b times 4. So we want \x to tell Python that this is going to be a hexadecimal address. So we want 08 \x 04 \x 83 \x F4, and then close our double quotes and close our single quotes. So now we have a times 9 plus, in hexadecimal, the return address is going to be the first address in overflowed. So we should be redirected to overflowed if we've done everything correctly. Since the program crashed, it says it's already started, so do we want to start from the beginning? We can say yes with a Y. We hit our first breakpoint. Again, that's in main. So we can look at ESP and EBP. Again, 12 bytes long, no change there. Go ahead and continue to the second breakpoint. And again, same size here for functions stack frame. And we have our 08048443 here. That's our return address. that hopefully string copy will overwrite correctly for us. So let's go ahead and continue to the third breakpoint. Alright, so we have our 41s, our 9As, and this should be our return address. If we disassemble overflowed, we should have 080483F4. And if we look at the command, that's what we told it, 080483F4. But if we actually look at our return address here, it's F4830408. What has gone wrong here? Well, it's not exactly backwards, but if you remember that in hexadecimal, 2 characters make up a byte, it looks like we're backwards byte by byte. So F4 is first, and it should be at the end. 83 is second. 04, and then 08. So again, byte by byte, it's backwards. If we remember back a couple videos ago, we had 141 off by itself. Well, we still do. It looks like it's the beginning here, and then we have other parts of our stack frame that have not been overwritten here. Then we had 41, 41, 41, 41, and then we had a null byte again at the beginning. So that was a little bit confusing, right? Why that happened, it again looked like things were backwards, and indeed, seeing this, it looks like there is really something that is turning things backwards byte by byte. So when I first started exploit development, I had no idea what this was. I had not paid enough attention in operating systems class, no doubt, and I was very confused, and I spent lots of time trying to figure out why my exploit wasn't working. So if you learn one thing about exploit development, just learn this. This is something called Indianness. So this comes from a book called Gulliver's Travels. Gulliver, on one of his travels, ends up in a place called Lilliput that has a war going on with one of their neighbors over which side of the egg you should crack. So people who say you should crack the big end of the egg are big Indians, and people who say you should crack the little end are little Indians. So we have kind of the same thing in computer science. So that is Indianness, spelled like this. So Indianness, so not like people from India or Native Americans, so with an E. So if you're not familiar with Indianness, I encourage you to Google it. There are white papers and Wikipedia and such. There are platforms that use Big Indian as well as platforms that use Little Indian. Never really come up with a good answer as to why one is better than the other. Everything I read in the white papers pretty much say it makes really no difference in terms of like speed and things that should matter to people who are designing chips. So as far as I can tell, it's really just a preference of the chip developers. But our Intel architecture here is Little Indian. Chances are most of the chips you'll end up working with are going to be Little Indian, but it may be big. You will, no doubt, if you try every platform you can get your hands on, run into something that is Big Indian where you will not have to flip the bytes around. But just as a good rule of thumb, I just remember chances are it's Little Indian. So all I need to do to take into account my Little Indianness is just flip our bytes around. So take the least significant byte and put it first, and most significant byte will be last. So again, just flip it around byte by byte. You don't really need to know the details of how and why this makes a difference to the chip. But again, if you're interested, I encourage you to look up Indianness. And if you can come up with a good reason why one is better than the other, then I can stop saying in my videos that it doesn't really make a difference. Alright, so easy to fix here. Let's go back to our run command and flip these around. Though we can just say continue, and it does indeed crash. So instead of going to 080483F4, it tries to go to F4830408. So again, it's backwards, and that's not mapped to overflowed, or in fact, it's not mapped to anywhere. So we again get our segmentation fault. So again, let's go up to our run command, and we just want to flip these bytes around. Not too hard to do. So we want F4 first, so least significant byte first. 830408. So this should work out nicely for us. So let's go ahead and run it. Again, we say yes to restart. And just continue through our first two breakpoints. We've pretty much got the drift of what's going on there. Hit our third breakpoint. Take a look at our memory. We have our 41s again, same place. And now our return address 080483F4. Taking into account Indianness did indeed fix our problem. So just try and remember your Indianness, and if things seem to be backwards, oh, I forgot Indianness, easy for us to fix, so you won't spend lots of time wondering what's going on like I did. So just a good rule of thumb. Alright, so now if we continue, it does print out execution hijacked to the screen. One thing to note though, after it prints out execution hijacked, we do receive the segmentation fault. It does crash. An ideal way to fix this would be if we had shellcode instead of just some function. We would use an exit routine to make the program exit gracefully. Whereas here we don't have any exit routine, so after execution hijacked is printed out, overflow tries to finish and return back to the previous function, which since we kind of screwed with things, it's just not going to work. So this is supposed to be the return address here, so it thinks it's returning back to main or to some function, but instead we jump over to overflowed, so we never save a return address. So again, this stack frame is going to be gone, this will be gone, that's what will load. So it naturally thinks, the program is just designed, or rather the platform is designed to think that this will be our return address, since it will be the top of the stack after overflowed removes its stack frame. So that should be the saved return address, but unfortunately it's just data from main plus should have a null byte at the end here. So it's like, okay, whatever. But the program just, blindly tries to execute that. It's like, okay, well, you're the top of the stack, you're the saved return address, so you must be this save return pointer, and sure enough, it's not mapped to anywhere, and we get a segmentation fault. We can kind of fix this in the short term if we want to. We could take our original return address and put it here. So that would redirect us into main, but we have destroyed main stack frame, so if you put the original return address here, of course in little Indian format, then you can see it will also print executed normally to the screen, but then again it will crash, it can't exit properly, so we've pretty much destroyed the program at this point, but we did make it execute commands on our behalf. Again, in this case it just says execution hijacked, not too exciting, but we will in our subsequent examples use some shellcode. We'll let MSF Venom generate it for us, and then we'll get a nice, more sophisticated working exploit. But again, I learned it this way. This was the first example that really made sense to me, so I do something similar. It wasn't the exact same program, but it was a similar notion of, well, we are supposed to go here, but instead we take control of the CPU and go here instead. So we get control of where we want to send stuff, and then we send it somewhere else. So, again, pretty simple example here, but I think a necessary building block for beginners to look at the other exploit development examples will do. So let's go ahead and do that. Let's switch over to Windows and look at a little more sophisticated example.